So the idea is that we're going to run our executable as a single argument to that is our binary blob with our shellcode, and then we just jump right to our shellcode, right, so we can test it. All right. The socket or the network-based version of that is very similar. If you look in the lower right-hand here, this stuff is all pretty much exactly the same. We still have a big buffer. We still create a pointer to it. And then we set up a socket ahead of time. So these things, like the port number you're looking for, those become important for your testing, but you can change them whatever you want. You just have to know what they are. So we set up a socket, and then again, basically, we're just doing our jump to the shellcode. So we set up an existing socket so that we can do things like find socket. Okay, assembly versus shellcode. Every shellcode payload has a distinct goal. It can't be non-deterministic, right? You can have, the idea is once it's become interactive, the shellcode's probably done. The goals that we're talking about here are pretty finite, pretty small goals. Something like open an interactive shell, that's where the term comes from. Add a user to Etsy password, edit a file a particular way. These are all common payloads and things like the Metasploit framework. There's also some other kind of hidden desirable goals. One big one is the absence of nulls, right? Everybody knows why nulls aren't there, right? Why can't we have nulls in the shellcode? Store copy, right? Because C-style strings are terminated with nulls. I need to go back and look at the first presentation today because he showed some shellcode and there were 3 nulls for every byte, and I have no idea what that was being used for. Must not have been going through any C-style functions, string-style functions. Oh, okay. Hey, he's right here. Yeah. No, I know. I should have been paying closer attention, I guess. That was too early. So anyway, absence of nulls, and then we have kind of a off the end kind of a goal of smallest size possible. So it depends on how you're getting your payload into the target, but the idea is that for generic purposes, you don't know how big the buffer is that your shellcode is going to be copied into. So the smaller your shellcode is, the wider range of targets it's going to work for, right? And we can get around these limitations with things like stage loaders and whatnot. But the idea is just to get it as small as possible because you don't know how big the buffer is. And then another common thing that a lot of people forget about, we have no file format. When we compile it, when we assemble this stuff, we end up with a binary blob. These are just the instructions that the CPU is going to be executing. So there's no like ELF header or anything wrapping around it. The ELF headers are designed for things like the OS loaders to know how to load all the information when you do it. Here we don't have a loader, right? We're just creating the actual binary. So getting the kernel to do stuff for you. So the kernel has predefined actions where you can ask the kernel to perform for you. How you formulate the question varies from system to system. These are normally called syscalls, and they have the 3 different ways we mentioned already: interrupt, farcall, and sysenter. So farcall. Most people regard far anything as a leftover from an antiquated segmented memory model that nobody uses anymore. Right? All of your popular OSs use what's called a flat model. So all of the virtual address space is addressable. The farcall not only specifies an offset in the memory, but it also specifies what's called a segment in the x86 architecture. And that segment, for purposes of this discussion, we can just think of that as some region of memory that's addressed in a different way. So we have this huge area of physical memory, and we can say there's a segment here, a segment here, and a segment here, and each of those have an offset 0. So they're not literal physical addresses, we've just named them in different ways. And we can also use those as permission-based things, right? We can not let certain subjects have access to different segments and so on and so forth. But anyway, all of these concepts relating to far jumps, far calls, far whatevers are pretty foreign to people. So for example, we can jump to offset 0 of segment 7. So we have our opcode for a far call, 9A. We have our offset, which is going to be relative to the segment base address coming from the GDT. And then we have our segment descriptor number. So this is going to be segment 7 in the GDT. So segments in general relate to regions of memory, but they don't have to. There's plenty of other types. So some have special types, like a call gate. So in a call gate, when we go to that portion of the GDT, an offset doesn't make sense because it's not a region of memory. This is going to be a method to get from ring whatever to ring 0, or to a higher privilege level, lower numbered ring. So this is a very common way to get from something like ring 3 to ring 0, right? And Just like the flat model, all contemporary OSs really just use 2 rings, right? Ring 3 and ring 0, and that's where you see these in all the presentations in the papers. All right, so the neat thing about call gates, everybody has them, or something similar. You need some method to get from ring 3 to ring 0, right? So we can get in discussions about IDTs and interrupt vectors and that kind of stuff too, but everybody has something similar to this. All right, the unfortunate or the sucky thing about syscalls is there's a lot of nulls in them, right? So by definition, you're probably going to have a pretty low segment selector. Nobody uses a segmented architecture, so there's no reason to have a full table of them. So there's very low numbers of descriptors in the GDT. And then the offset for something like this is always going to be 0, because you're never jumping into the middle of a memory segment. This is just a gate to get to something else. So the offset's always going to be 0. So we have a bunch of nulls. And the nulls are not good for shellcode. So these are normally manufactured as part of your payload, as part of your shellcode. And you can do something like make your shellcode FFs and then knot them to have the processor turn all the 1s to all 0s. And then you've kind of manufactured yourself nulls in that way. Unfortunately, creating this is very expensive. So ideally, you only do it once and then you save a pointer to it basically. And you can call your pointer repeatedly later. Even if you do that though, you still have all this wasted time that you have to use to generate this, this function, so to speak. And then there's this other method. Intel observed fairly early that syscalls happen a lot. So they made this fast system call instruction, sysenter paired with 6exit. Basically, it does the same thing. Intel claims it's a lot faster, and it has some caveats to it. You have to kind of set things up just right before you make the call. You need to put some stuff in EDX, put some stuff in ECX. Your function that you're manufacturing is basically going to end up looking like what you see down here. So similar to the FAR call, this is expensive to manufacture in your shellcode, right? You're wasting precious bytes in your shellcode setting something up. If we don't have to do that, it'd be much better. All right, and the final method, the third method, is with a software interrupt. So just like your keyboard and your mouse and all your other hardware that generate interrupts all the time, we can generate an interrupt in software with an instruction called int, e.g. int80. That's what a lot of OSs, or a lot of the Unix-based OSs use. So this will basically raise an interrupt to the CPU similar to a hardware interrupt, and that will be used as an index into a table called the IDT, an interrupt vector, and then that will then locate code that will execute and actually handle the syscall. So the int80 is just used by convention. It's really just an index into this table, so it can be whatever. So this is pretty much as good as the PowerPoint foo gets in this presentation. I don't have any cool pictures like the last guy. So we have this table. Interrupt software occurs. We see the int80 happening on the left-hand side. When the interrupt occurs, several things are going to happen automatically as a byproduct of the interrupt. The CPU is going to push a whole bunch of stuff on the SAC, among them CS, eFlags, EIP. If you haven't written interrupt ISRs, interrupt handlers, basically you save state when you go into the interrupt, and then you handle your interrupt and you muck with the registers as you're performing everything, and then you restore state right before you go back. Across a system call, most of that stuff comes back except for the return value from the system call. So normally in EAX, but as we'll see in a second, sometimes other registers have like different return values as well. So this 80 is an index in the IDT. This blue box will say that the physical memory address here is the base of your IDT. There's certain predefined ones for things like divide by 0, special exceptions that the processor handles. So if you do a divide by 0, it'll index into here, and then you still have to handle that. It's just this vector is predefined, right? You still have to have it make your ISR that says page fault can be handled this way, or whatever. The rest of these are all user-defined, so they can have whatever meaning you want. So 80 indexes into somewhere, we get this descriptor. This descriptor has 2 portions for our purposes. One is, whoops, gotta watch that. One is an offset to a segment. So in a non-segmented model, this might be a linear offset, but it's still an offset to a segment. The other, a descriptor, so we can find the base of our segment, and then this other piece is an offset into that segment, which finds the code that actually handles the syscall. All right, so Not super important to understand exactly where the arrows go or whatever, but interesting to know that interrupt comes in, finds a vector in the table, and the table tells you how to find the syscall handling code.